This is JEE Advanced 2020 paper 1 of section 3, and this section contains 6 questions. The answers to each questions are numerical value type of questions, and up to 2 decimal places you have to truncate off and round off the figure and give the results. So let's start right after this short break. And if you're first time on my video, then please like, subscribe, and don't forget to hit the bell icon button to get the video first.
Audio Jungle. Audio Jungle.
Section 3. Question number 13. Put a uniform meter scale horizontally on your extended index finger, with the left one at 0.00 centimeter and the right one at 90.0 centimeter. When you attempt to move both the fingers slowly towards the center, initially only the left finger slips with respect to the scale and the right fingers does not. Okay. After some distance, the left finger stops and the right one starts slipping. Then the right finger stops at a distance XR from the center, 50 centimeter of the scale, and the left one starts slipping again. This happens because of the difference in the friction forces on the two fingers. The coefficient of statics and dynamic frictions between the fingers and the scales are 0.40 and 0.32 respectively. Then the value of XR is. Okay, so in this question, first of all, you have to make the FBD of this one rod for this one as the center is at 50 centimeter from left. So initially, from the right, the fingers are slipping towards. So from right, friction force will be towards left, and from left corner, friction force will be from right corner. So in this way, after equating this one parallel forces, you can apply this one frictional forces, counter this friction forces, as due to this along with the rod, you see the net force will be 0, and from along with the torque, you can say, or any other points you say, better just you consider on the center, you can make the net torque also is equal to 0. So it means rotational equilibrium and translational equilibrium concepts to be carry on. So by using this, one can find here XR. So this will be our strategy to solve the problem. So let's start. So first of all, you have to make the FBD, free body diagram of the rod, and from one end initially left, that is N1 reaction force, and N2 reaction force from rightwards 50 centimeter. This is center nodal point, and this is 40 centimeter after shifting this one 10 centimeter from right. So by balancing torque, we can conclude that N2 is greater than N1. So F2 is also greater than F1. So that's we say, as the rod does not move so over here, that we call here, does not move, only left finger slips as according to as per problem. So what we say here, net external force, F net is equal to 0, you say. So F translational consideration, so friction force F mu s into N and mu k, that is N6. So mu k N3 and mu s N4 in the previous case. This one mu k N3 and mu s N4. This force to be counters. So that's why they make it equal, equation number 1. And not net torque, that is about the center, that will be X1 N3 and 40 N4. This one X1 N3, and here that is force into perpendicular distance, that is 40. So that's equal, and this by the equation 1 and 2 on dividing, we get X1 equal to 32 centimeter. Now draw this one FBD, that is N5 and N6, assume this force as leftwards also shift towards here. So in this situation, F net equal to 0 and mu s into N5 is equal to mu k into N6. So now in this case, leftwards we carry on static friction, as here finger is not moving over here, and in the right side there is a dynamic friction, that is frictional force. So mu s N5 and mu k N6, that is the point to be noted over here. And mu s and mu k, this is given the question as 0.40 and 0.32 respectively. And here also, once again, applying torque net equal to 0. So N5 into X1, and here that is N6 into XR, that is equal. So that is equation number 4. Now about the center, we are using this torque in the previous one also. Now dividing equation 3 and 4, you will get this one 0.40 upon X1, 0.32 upon XR. So in this way, we can find the value of XR. So XR is 25.60. That's the answer. So 25.60, as this is single digit integer type question. It's up to decimal 2 places you have to write. So you have to write this 25.60. Now question number 14. When the water is filled carefully in a glass, one can fill it to a height h above the rim of the glass. Due to surface tension of water, to calculate h just before water starts flowing, model the shape of the water above the rim as a disk of thickness h. Okay, this is the h given. Having semicircular edges, having this one, semicircular edges as shown schematically in the figure. When the pressure of the water at the bottom of this disk exceeds the what can be withstood due to the surface tension, the water surface breaks near the rim and water starts flowing from there. If the density of the water, its surface tension and the acceleration due to gravity are 10 power 3 kilogram per meter cube and 0.7 Newton per meter, so that is, and 10 meter per second squares respectively, the value of h is. So here, that is the strategy to find using the surface tension. That it means after balancing this one force ATM into this one P average, that is h height. Let the height be h, this one, and the radius is r as given. So 2 pi r, you can use this one on the periphery here, and surface tension into 2 pi r. So you can get the value of surface tension. With the help of this, you can find the height h. So this is the strategy to solve. Now on this surface here, as a semicircular surface, so P average into area is from one side, and another side P ATM above ATM pressure into area. So equating this as into 2 pi r and balancing with this effect of ATM pressure on both sides, P average into h into 2 pi r. So that is S is equal to rho hg upon 2 into h. So 2s upon hg is equal to h square, and this, substituting these values, surface tension as given in the question, and substituting, you will get the value 3.74. Now question number 15. As in the question number 15, one end of a spring of negligible unstretched length and spring constant k is a fixed at the origin 0 0. Okay, this one 0 0. A point particle of mass m carrying a positive charge q is attached at the other end. This one. The entire system is kept smooth horizontal surfaces. When a point dipole p pointing towards the charge q is fixed at the origin, the spring gets stretched to length L and attains a new equilibrium position according to figure. If the point mass is not displaced slightly, del L is very less than L from its equilibrium position and released, it is found to be oscillates at the frequency 1 by this del, known as Kronecker del, under root k by m. Then find the value of Kronecker del is equal to question mark. So in this question, what do you have to do? Here the potential energy of this stored in the spring, that is half of kx square, and we will go for this one to solve this frequency. So frequency, that is 1 by 2 pi under root k by m. So for this k, as you know, d square u by dx square you can find here. So as spring energy is u equal to half of kx square, you double differentiate, you can get the value of d square by u upon ds square, and in this way we can get the frequency, that is 1 by 2 pi under root d square u upon dx square upon m, you can say. So in this situation, on this, according to Hesper's concept, the system from equilibrium as given negligible unstretched spring. So the spring length is elongated, and length only be this one U is equal to, so in this situation stored energy will be half of kx square plus this one pq upon 1 by 4 pi epsilon naught, you say here this one, and that will be x square. So according to this, once again you can find the potential energy here in this one, and by using this equilibrium you can find this frequency in both the cases. So let's start this one. So this is, let's assume that length is L over here of the spring, and as you know, the spring block system F equal to 1 by 2 pi under root K by M. This can be K can be evaluated by making double derivative of potential energy as U is equal to half of Kx square. So differentiating single derivative, that is Kx, and double derivative, that is K. So we can substitute over here and find the frequency by 1 by 2 pi under root d square U upon dx square. Now substituting this potential energy, and so for the above concepts, let's PE U of the system for equilibrium as given negligible unstressed length. So the spring is elongated length only this much. So that's why Q is the charge over here. So for equilibrium position, what we say here, the entire potential energy is half kx square is stored in the spring, and the energy is stored in this one charge due to this charge. So that is P into Q upon 4 pi epsilon naught x square. That is 1 upon 4 epsilon naught Q1 Q2 upon R. Here P, Q, and x square. X length is the length elongated. So du by dx differentiated here, that will be kx, and here after differentiating minus 1 by x minus 2 upon x cube, that will be, so 2pq upon 4 pi epsilon naught x cube. For equilibrium, du by dx equal to 0 as given equilibrium at x equal to L. So you can say this will be KL, and equating this potential energy. So that will be d square u upon dx square, differential equation. One will become this one, d square u upon dx square, instead of kx, what we say, that is k, and here plus 6 pq upon 4 pi epsilon naught x to the power 4. Yes, after double derivative of this one, differentiating first equation 1. So as equilibrium at x equal to L1 d square u upon dx square, substitute the value of x is L over here. So k plus 6 pq upon 4 pi epsilon naught L to the power 4. So from this equation 2, now you can submit this value, convert this in terms of k and L here. So as you know, 2pq upon 4 pi epsilon naught L cube, that is KL. So for this 6, you can say 3k. So k plus 3k, that will be 4k, and hence F equal to as d square u upon dx square, that is 4k. So in this numerator position, you just submit 4k. So you will find 1 by pi under root k by m. Question number 16. Consider 1 mole of helium gas is enclosed in a container at initial pressure P1 and volume V1. It expands isothermally to the volume 4V1. After this, the gas expands adiabatically and its volume becomes 32V1. The work done by the gas during the isothermal and adiabatic expansion process are W iso and W adia respectively. If the ratio W iso upon W adia is F ln2, then the value of F is question mark. So what will the strategy over here? As you know, here this is the isothermal process, and then after there is adiabatic. So there is a combined situations. So for adiabatic you have to account here, and for isothermal also you have to account the work done. So for adiabatic, that what you have to find, you have to find the temperature, because the formula for adiabatic is nR T1 minus T2 upon gamma minus 1. So for that T1 and T2, you have to use this one formula for adiabatic Poisson's ratio, that is TV power gamma minus 1 is equal to constant. And for this gamma, what you have to use here, for gamma you have to, as this gas is, you have to check the gas, 1 mole of helium gas is there as monatomic gas, so gamma will be 5 by 3, okay, for monatomic gas, and submit this value, and you can find the adiabatic work done. And isothermal work done can be evaluated as nRT ln V2 by V1. So for this one isothermal, you will use Boyle's law as P1 V1 is equal to P2 V2. In this way you can find the ratio of the volumes, and in this way you get the isothermal and adiabatic. Very easy problem. You can solve this very easy manner. So let's start. As this is isothermal process, P1, V1, T1 for helium gas, and this is the adiabatic say. So after this one 32V, and here after when thermally it is expanded, so volume doubles 4V. Later on we will calculate about isothermal. First of all we go for adiabatic, let's calculate. So T1 TV for gamma minus 1 is equal to constant, as gamma will be 5/3 for helium gas, monatomic as it is. So what we say here, T dash is equal to T1 V1 to the power gamma minus 1 upon T2 V to the power gamma minus 1, as 32 V is there, and initially 4V was there because first of all isothermal and then adiabatic they are expanding. So from isothermal to adiabatic, so V1 will be 4V and this one will be 32V. So we can use this one 4V1 and 32V1, and this retaliated, so that is 1/8 to the power 2/3, 5/3 minus 1, that is 2/3. So finally that is T/4. So using this T/4 as the formula for W, that we say W, as you know, the W for adiabatic will be NR upon gamma minus 1 into T1 minus T2. Yes, so submit this value over here, and R instead of T, that is T1, that is T, and T2 we have already calculated over here, that is T/4. So submit this value T/4 over here, and gamma, that is 5/3. Substituting this value, we find N by 9/8 nRT. Now for work done in isothermal process, nRT ln V2 by V1 by multiplying 2.303, you can put log base 10 also, but no need to do over here because ln2 you all know well the value, as in the question it is whether given ln v2 ln2. Yes, ln2 is question is in terms of ln2. If you see here, the question is in terms of ln2, so no need to write 2.303 log, better ln v2 by v1. So nRT ln 4v1, that is final volume, and initial volume was let v1. So after retaliating, you find here ln4, and ln4 can be written as 2 ln2. So 2 nRT ln2, and on dividing with this by 9/8 nRT, which we have calculated for adiabatic, that is 2 nRT ln2 upon 9/8 nRT, we find 16/9 ln2. So 16/9 will be the answer. After solving decimal 2 places, you will find 1.77. That is your answer. Now let's go for another question. That is question number 17. So question number 17 belongs to question, you see here it's given as like this way, this a Doppler effect. So question number 17 is from Doppler effect. A stationary tuning fork is in resonance with an air column in a pipe. If the tuning fork is moved with a speed of 2 meter per second, and in the front of the open end of the pipe and parallel to it, the length of the pipes should be changed for the resonance to occur with the moving tuning fork. If the speed of the sound in air is 320 meter per second, the smallest value of the percentage change in the required in the length of the pipe is. So for here, for open pipe, the resonance, that is F equal to NV upon 4L you have to use. So L is the length of the initial length of the pipe, and N you have to put 1. So F1 will be V upon 4L, and hence for F2 you can see over here, you can apply Doppler effect as V0 minus 0 upon V0 minus Vs, like this way, into F1, and in this way you can calculate F2. So dividing F2 and F1, you will find this the ratio of the length, and hence you can find the percentage length, that is delta L upon L into 100%, that you have to solve. So for open organ pipes, let's start. For open organ pipe, F equal to NV upon 4L, for N equal to 1 here you have to put, and for L, that is L1 for F1, so F1 will be V upon 4L1, and F2 we say 320 upon 320 is this one, it should be given over here. 320 is sound in air, 320 meter per second, although it is given in the question. So 320 upon 320 minus 2 you have to use. So this one is F1 and F2. Now what you have to do here, you have to simply divide this 322 minus 2, that is 318. So 320 upon this one will be 318. So 320 upon 318 into, on dividing this two equations. So let's see, F2 is equal to 320 upon 318, F1 2 by this is equation 2, and F2 that will be V upon 4L2. So what we find over here, on using this one 2 and 3 equations, we find v upon 4 L1 into 322 upon 318 is equal to v upon 4 L2, and hence we find L2 by L1, that is 318 upon 320. Now change in the length upon total length, that is the ratio percentage change. This ratio you can find here, and here after multiplying, submit the values here 100, that is 5 by 8%, nearly 0.625. So up to decimal 2 places we have to submit the result. So that is 0.62 is your final answer. So let's go for another question. Question number 18, that is a circular disk of R carries a surface charge density sigma R and sigma naught into 1 minus a small r by capital R, where sigma naught is constant and R is the distance from the center of the disk. Electric flux through the large spherical surfaces that encloses the charged disk completely is phi naught. Electric flux through this one, another spherical surface of radius r by 4 and concentric with the disk phi, disk is phi. So the ratio of phi naught to that of phi is question mark. How to solve this? As you know, that is phi is equal to q enclosed upon epsilon naught. It's from Gauss law. So question is from Gauss law chapter. That is a very easy over here, and nothing to do over here. That is q. After on, later on, you have to integrate for the entire charge from 0 to r. That is sigma naught into 1 minus a small r by r, 2 pi r. You can use as surface area for that, and dr, and then integrate this one. So let's start. That is, charge in the elemental ring is r naught 0 to r is equal to 0 to r sigma 2 pi r dr, from here 0 to small r for this ring here. Let this be disk over here. As phi naught is equal to, this is the formula for Gauss law, q enclosed upon epsilon naught, and q enclosed, that is here q you have to find first. So 0 to r you have to integrate this. Sigma is given over there, sigma naught into 1 minus r by r, and that is 2 pi r dr. And now integrate this. So r dr, that is r square by 2 integral, r square integral is r cube by 3, and that is 2 pi sigma naught common, and that is capital R left over here. So for phi naught, that is r equal to r, q enclosed is equal to, you can find 1 by 6 2 pi sigma naught r square, and hence you can find at small r equal to r by 4, that is q dash is equal to 2 pi sigma naught r by 4 whole square by 2 minus r by 4 whole square, as these are the results over here. Upper limit and lower bound, r by 4, that is r by 4 whole square by 2, and r by 4 whole cube by 3r. And then finally, after solving this all and substituting the data of capital R over here, as you know, phi naught upon phi, you will find 192 upon 6 by 5. These are the calculation you can do over here. 6.4, nearly answer is 6.4. So this is pretty easy, nothing to be bothered about this. Okay, thanks for watching.